Welcome to Excel 2013 Statistical Analysis video number 72. Hey, if you want to download this workbook for Chapter 11 and follow along, or you want to download the PDFs, click on the link below the video. Hey, in this video, we're going to talk about hypothesis tests to check the equality of two or more population proportions. And we're going to be using a new distribution and a new test statistic called chi-square. Here it is. That's the symbol we're going to use. And it's pronounced chi like pi. So chi-square. Now, before we talk about this, I want to page down in the PDF and look at an example. This is an example of a hypothesis test for equality of two or more population proportions. And by the way, the textbook says 3 or more, which is fine. Most of the time you use this test for 3 or more. But I put 2 or more because you can do it for 2. Here's our question. An executive, an HMO. Oh, this is like our last example in last video, but in there we only had 2 populations. Executive of HMO wanted to check the accuracy of patient contact information. A sample of patient records was taken for each of the years 2011, 12, 13, and 14. Are error rates the same for each year? These are called the observed frequencies. And notice this is like a cross-tabulated table. We're always going to put our categorical variable in the rows, and then we're going to put our populations across the columns. So we have a yes and a no. Because remember, we went out and did a sample and checked accuracy. They either had an error yes, or they didn't have an error no. Here's 2011, 2012. 2013, we had 45 sets of records that had errors out of a total of 316 sampled. Now, what we're really interested in is the proportions. And if I were to take 39 divided by the sample size for this first population, I would get this proportion. That would be P bar 1. In 2011, we sampled and got 11.4% error rate. Then in 2012, I take the 43 divided by the sample size from population 2. And P bar 2 would be 43 divided by 266. That would be the proportion. Wow, 16.2. So we have like 11.4, 16.2, 14.2, and 10.7. We also want to calculate the overall. So the overall error rate for all 4 years is 12.9%. Now, this is the overall rate. So if these were all the same, they'd be 12.9. That means each one would be 12.9, and there'd be no difference at all. Now, we'll come back and start here in just a moment, but I'm going to page up, and talk about the chi-square distribution. Here it is. It's a probability distribution. The area under the curve is area. All of it equals 1. It's going to be our probability. Now, like the t distributions, we're going to be using degrees of freedom. There's degrees of freedom 1, degrees of freedom 3, degrees of freedom 10. Now, you can see when we have very small degrees of freedom, the actual distribution is shaped a lot different. If we get up near 10, then it approaches a bell shape. Now, that means we have a family of chi-square distributions based on degrees of freedom. K is going to be defined as our number of populations, and R is going to be either rows or number of categorical variables. Remember, just a moment ago, we saw yes and no. So the 2 categorical variables, or we could think of it as rows in our cross-tabulated table. Our degrees of freedom for 2 categorical variables is simply population minus 1. If we have 3 or more, we take the actual rows or number of categorical variables minus 1, and then multiply that by populations minus 1. So this is the distribution, right? And here's our chi-square test statistic. That's what we'll get busy calculating when we're running a test. Now let's jump to our next page down. This is a list of all the variables we're going to use while we're calculating chi-squared. These are the population proportions from 1 all the way to k. There's our number of populations. That's our number of rows or categorical variables in our cross-tabulated table. Here's our sample proportion, degrees of freedom, and we're going to use f sub ij The I just means the row, J just means the column of our observed frequencies. And this will be a calculated number, expected frequency. And since it's a cross-tabulated table, to figure out where the expected frequency or the observed value is, you got to know the row and the column. This will be our chi-squared calculated test statistic. This is the one that will take lots of calculating. And then here's our critical value. We'll use alpha because actually our test will always be on the upper end. Given that we're using a cross-tabulated and the smallest number we can ever get is 0, it's always going to be an upper test. So we're going to throw our alpha, our risk that we're rejecting the null hypothesis even though it's true, will always be on the upper end. So we're going to show chi-squared with alpha to mean our critical value. Now notice here's our little diagram, right? Whichever shape it is, we'll still have, like we did before, a line, and that separates. Up here, we reject the null and accept the alternative. Below it, we fail to reject. Now I'm going to page down and go to our next page. Hey, this is where we started off. This is our cross-tabulated table with our yes, there were errors, no, there were not errors. And there's each one of the populations, which is each one of the years. There's the sample size. We talked about these proportions, 4 different sample proportions. Now, all of these sample proportions were different. But remember, some difference sampling error is acceptable. We need to check for significant difference. And that's where calculating chi-squared with observed frequencies and something called expected frequency comes in. Let's page down. Now, before we look at the formulas, it'll be easier if we look at a simple logical example of how we might consider calculating an expected frequency. The essence of how we will check to see if there's a significant difference in proportions is by comparing our observed frequencies and our expected frequencies. Now, observed frequencies, here, this is the yes in 2013 from our cross-tabulated table. There it is, 45. Now, think about this. Remember, just a moment ago, we said if we took 168 divided by 1307, that's this right here. This would be the overall probability for yes, 12.9%. Well, if we had some number right there that when we took it and divided it by 316 equaled this 12.9%, boom, we'd have exactly the same numbers. That would be our expected frequency if all of the proportions were the same. So here's how we're going to do it. We're going to take 168 divided by 1307. There's our 12.9. Then we're going to multiply it. Here's 2013, and that's the sample size. If we take 12.9% and multiply it by that, it'll give us exactly the number that should go right here that would be expected to give us this 12.9. So down here, if the yeses in 2013 were equal to 12.9%, then, hey, 316 times this 0.129 would be exactly equal to 40.6. And we can check this to see 40.6 divided by the 316 equals exactly 12.9. Now, that's just kind of common sense, right? We got the proportion comparing the 168 to the 1307 for overall yes, multiplied by this, and got a number, not 45, but 40.6. That is the essence of what we'll be doing for our calculations of chi-squared. Now I'm going to page down, and we're going to talk about the 5 steps for a hypothesis test to check equality of 2 or more population proportions. Hey, our null and alternative, we're going to say that all of the proportions are equal. Our alternative will say not all proportions are equal. This really means 1 or more population proportions differ from the other population proportions. This test doesn't actually figure out which one. It's just seeing if they're all equal, yes or no. Step 2, we're going to have step 2a and step 2b. Well, we know step 2, we set our alpha. That's the risk that we reject the null when it is actually true. Step 2b, we're going to select a random sample from each of the populations. That means for each year getting our yeses and nos, and create a cross-tab table with observed frequencies. Now, the observed frequencies, as we mentioned, is going to be F for frequency, observed frequency, row I, column J. I is the row, column is the J. So here's our table. If we were going to ask the question, where is frequency for row 1, column 3, we would go to row 1, column 3, and that intersecting value gives us our 45. This is the notation that they're going to use for observed frequencies. Now let's page down. Step 3, we're going to assume that HO is true. That means that all the proportions are equal. That means that 12.9%. And compute expected frequencies E sub I sub j. I is row, j is column. And here's our formula. But we already know how to do this, right? It says row I total divided by sum of all sample sizes. For yes, this whole row is yes. There's the row total divided by the sum of all the sample size. That gives us the 12.9. So we're going to do that actually for the yes row and the no row. Then we simply multiply it by the column total. We already saw that. The column total is the sample size. It's actually the total for all the no's and all the yeses. Every single cell in our table for the yes for all the years and the no for all the years will use this formula. Our example, expected frequency row 1, column 3. There's that percentage times the sample size. Boom, we get 40.6. We're going to have to do that for each one of the cells inside the table. Now notice something. This looks like a lot of calculating. But that's what Excel is for. Notice column, 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 row, row. It'll be easy in Excel. Now let's page down. This is still step 3. Page down. We do have step 4. And before we can proceed, we actually have to check every single expected frequencies to see if it's greater than or equal to 5. Now notice we've seen this checking for greater than or equal to 5 with proportions a few times in our book. And here we have to do it again. Every single one in our case is much bigger than 5. So we're perfectly fine to proceed. Chi-Square Test Statistic. There it is, chi-squared. We're simply going to take the sum of all the rows and the columns. And here's our calculation. We're taking observed frequency minus the expected frequency. Hey, that's sort of like a deviation. We're going to square it and compare it to our expected frequency. If we add every single one of these up for our table, boom, we'll get our chi-square. That is the calculated test statistic. Then we can go with our alpha and calculate the critical value and compare them. Now notice, here's every single one of the values in our table. If we did this calculation all the way through for row 1, column 3, we'd get, oh yeah, that's the observed frequency 2013, yes. There's the expected frequency 2013, yes. Subtract them, square it, divide by the expected for yes 2013, and that's the number right down in the table. Now let's come back up here and think about this again, just in simple terms. That's the observed, but what are we subtracting? That's the expected frequency if the percentage was exactly 12.9%. So when we say observed minus this, we're saying how far is the observed from the value that would give us exactly the same proportion for each one of the populations. Then, of course, we square it and compare it to, again, the value we would expect to get if the percentage was exactly 12.9%. Now, this is step 4A and 4B. If I page down, we're actually going to have 4C, which is some more calculating. There's our alpha. K is the number of populations. We need our degrees of freedom. And we only have 2 categories, so we simply take K minus 1, our chi-squared critical value. Oh, look at that. There's a chi-squared function. Dot inverse, we know by now that means the value. And because it's always on the upper end, it's going to be a right. We simply put our alpha and degrees of freedom, 0.05. Degrees of freedom are 3 because we had 4 populations minus 1. And there is our hurdle, our critical value. Obviously, that's way past. So our calculated test statistic did not make it by that. We're also going to be able to actually skip this step And once we get our expected values and actual values, we can use the chi-square-test function. And this is much different than any function we've used. We're going to use table of observed frequency and the table of expected frequency. Slap those two in, and it will spit out the p-value. Now notice if alpha is 5%, this p-value is huge compared to that. So in both cases, we would fail to reject. Now, just to be consistent, remember, anything with an inverse is the value. Anything with a dist is the probability. So if we calculate our calculated test statistic, which we got to be 5.35, we can use the chi.dist probability dot right, because it's always upper, and it will spit out the same exact p-value. And then we will come to our conclusions. Now let's jump over to Excel. We're on the sheet 4 p-bar chi-squared. Now here is our data set, and it is not an actual proper data set per se where we could do a pivot table. If I, in 2011, control down arrow, notice I had 343 here. If I control up arrow in B column, you can see the last value was 267. So that means control up arrow, we would have minus the field name 266. That means that each one of these ranges has a different number of cells, not a proper data set. So we're going to use formulas to get at each one of these columns to count the yeses and the nos. Now, our first step, of course, is the null hypothesis. All of the population proportions for yes, there's an error are equal. The alternative hypothesis will be not all proportions are equal. We have an alpha of 0.05. I is row, J is column. It looks like it didn't want me to have a capital there. There we go. Now I'm going to show you a different type of cell reference in our formula. Now this is just a straight COUNTIFS. I need to count all of the yeses and nos for 2011, all of the yeses and nos for 2012, etc. So I'm going to show you a different type of cell reference because I don't want to calculate 1, 2, 3, 4 different formulas. So you ready? Equals COUNTIFS. And I'm going to highlight for the criteria range the column header, the letter A. And watch what happens. It instantly says A colon A. That means the whole column. Now, in order to use a column reference like this, you can't have any rogue data below our data set. And we don't here in this case. Now, the nice thing about this is when I copy it down, it will not move because that's the entire column. When I copy it to the side, it will move to B and then C and then D, comma. Now, the criteria range. If I click just on yes, if I copied it down, the relative cell reference would move to no. But if I copied it to the side, the G would turn to an H. So I'm going to use what's called a mixed cell reference for our criteria cell. That means it's going to be relative when I copy down. So it will go from 11 row to 12 row and pick up the no. But when I copy it to the side, the G will be locked. So as I copy it to the side, the orange one will be locked there. Now ready? We've hit F4 before. It puts in both dollar signs, row and column. I'm going to hit the F4 again and the F4 a third time. Dollar sign to lock only the column, but not the row. Now watch this. This is beautiful because now I only have to create one formula, Control Enter, copy it down one, let go, and then re-grab the fill handle and drag it to the side. And watch this. When I click in the last cell and add F2, it got the exact right D column, and it's got the exact right G12 for no. And notice in this whole row, it's locked on the G12 for no. But if you look up here, it's got the G11. That's called a complete column reference for here. And that's a mixed cell reference with the column lock, but not the row. Now I want to show you a different trick here we haven't done before in the class. I want all the totals here and all the totals below. So I'm going to highlight the numbers. and then some rows to the side and some rows below. When I use our keyboard for the auto sum, Alt equals, it knows perfectly to put in the sums. Look at that, F2, F2. That one's adding up all of the sample sizes to get the sum of all the sample sizes. Hey, look, there's our 168. There's our 1307. There's our 45. Now, I want to calculate our sample proportions. And I'm going to use mixed cell references here. Now, equals, hey, I'm going to go ahead and take yes for 2011. When I copy this down and over, I want it to move relatively, so I'm leaving it alone. Divided by, and I want the H13, when I copy down, I want it to remain locked on H13 because that's the 13th row. But when I copy to the side, I want the H to move to I and then J. So watch this. I'm going to hit the F4 key once. That's absolute, locked in all directions. Twice, locked only when I copy down, but not to the side. Notice that's exactly what we want. That formula for yes and no needs to be looking at that number. But when I copy to the side, it needs to move there. Control-Enter, copy it down one, let go. Re-grab the fill handle, copy it over to the side. Go to the diagonally furthest one away and F2. That is amazing. That's the use of relative cell reference and mixed cell reference with only the row locked. And again, you could test it out. It works perfectly. Now, I want to highlight the table. We're going to do that same trick with the auto sum keyboard. There's a row below. So when I Alt equals, it knows to add perfectly the cells above. Now, I want to calculate our expected frequencies. Now, a formula for expected frequency, here it is. We're going to take row I total and divide, so whichever one of the two yes, no totals, divided by the sum of all the sample sizes, boom, times the column J total. Remember, the first part here is really the overall proportion for yes and for no. So I'm going to calculate that off to the side. I'm going to say, hey, the 168, and that'll be relative. So when I copy down, it'll move to 1139 divided by the sum of all the sample size, F4. Control-Enter, and drag it down. That's approximately that 12.9, and this is 87.1. So we're going to actually take each one of the column totals, which are sample size, times the overall proportion for yes. Again, the idea is we've already calculated that little bit for the whole row right there. So you ready? Equals, and I'm going to say there's the proportion. Now, when I copy this down, I need it to move. But when I copy to the side, I need it locked. So I'm going to hit the F4 key 1, 2, 3 times. Notice the M23, the 23 doesn't have a dollar sign. That's an M23. So when I copy it down, it'll move to M24. But when I copy to the side, boom, it's locked on M. So that's the first part there. Times, here's our column total. That's the sample size. When we copy it down, I need it locked on that 343. But when I copy it to the side, I need it to move to 266. So here I want it locked when I copy down, but not to the side. I hit the F4 key once and twice. I'm locking just the row reference 13, but not the column. Ready? Control-Enter. Copy it down. Copy it over. And there we go. Go to the last diagonal one, hit F2, and admire that. It got it exactly right. There's the column total, and there's the overall proportion for no. And again, you could check any one of these. I know this is the first time we've used mixed cell references, but it's just too good of a trick not to. It saves us time. All right, now we can add these up, and expected better be exactly equal to our original sample size. I'm going to highlight the table and Alt equals. And sure enough, each one of those adds it up. Now we can calculate, start to calculate the individual pieces for our chi-square calculation. We need to calculate the deviation in essence and square it. So that's what I'm going to do right here. Equals, I need the observed frequency minus the expected frequency. And notice those are relative references. So down and over, it will work perfect. Close parentheses and caret 2. Control-Enter. Copy it down and over. We're now going to come down here. This is the numerator, in essence, before we divide it by our expected frequency. You ready? Equals There's that, in essence, deviation squared, and we're going to divide it by our expected. That whole little top part right there is the blue one right there, divided by the expected frequency. That's right there. These are relative cell references. Control-Enter. Copy it down and over. Now notice I wrote deviation squared divided by expected frequencies, but these are actually the final calculations to add to get our chi-square. So here's the drum roll. Test statistic chi-squared. I come over here. Alt equals. It didn't guess right, but no problem. Now I simply highlight these. Control-Enter. That is our calculated test statistic. Now here we did two subtables before we summed. If you just had your expected frequencies and your observed, we could do it in a slightly shorter formula. We've done sum product a bunch of times in this class. Remember, our formula is ultimately observed minus expected. So right inside parentheses, I'm just going to highlight all of the observed, subtract all of the expected, close parentheses, caret 2. If I were to highlight that entire array and hit F9, you could see that 25, that 77. That's exactly the values we got there, but all in our formula. Control-Z. The final step is that we need to divide by expected. So we simply divide, and here's our expected. And that's it. Close parentheses, Control-Enter, and it will calculate it. There's still one other formula that I wouldn't use if you didn't want to do expected. And there it is. This formula only relies on the observed frequencies. But again, I don't think I would use that one there. Now we have a few more calculations to finish out this hypothesis test. We do need to count our populations. I'm going to use equals count, because I'm counting numbers, and I'm actually going to highlight the original observed frequencies. Those are the column headers, the populations, and enter. That gives us a 4. Our degrees of freedom, I'm going to take that 4 minus 1 and enter. Now, there's two ways to calculate p-value. We can calculate p-value once we have our calculated test statistics and our degrees of freedom. Equals, and we're using chi. And if we're calculating a p-value, which is a probability, we're going to use the dist. And this is always an upper test, so I'm going to use the chi-dist right. All it wants is the actual calculated test statistic, comma, and the degrees of freedom. Remember, there are many different chi-square distributions, so this tells this function which distribution to go and look at. And of course, this will tell us the probability of getting that value or more. It is huge. If we compare that to our original alpha up here, we fail to reject the null hypothesis. Now, if we want to do our critical value equals, well, it's the chi-square. And we're using the inverse because it's a value we're calculating, and it's always on the upper end, so we use right. The probability, oh, this is our risk, alpha, comma, and our degrees of freedom, close parentheses. Now we can match this up, Control-Enter, with our calculated test statistic. This is the hurdle, the critical value. Our calculated test statistic is not past this. Now, the fastest way to do all this, I showed you all of this so you can choose which way you want. But you are going to have to calculate observed and expected at minimum. If all of these are 5 or greater, we can use this awesome new function, equals chi-square, but it's not inverse or dist, it's test. And we put the actual range, which is observed values. I'm going to highlight. There it is, the actual range, comma, and our expected range. That's our expected frequencies that we calculated. Close parentheses, and it calculates p-value. So the shortest way to do your hypothesis test is simply to calculate observed, your expected frequencies, and then use your chi-square.test. Our conclusion is, hey, because our p-value is bigger than our alpha and the test statistic is not past our critical value, we fail to reject the null hypothesis. It's reasonable to assume that there is not a difference between the population proportions. Another way to say this, the statistical evidence suggests that there is not a significant difference between the population proportion. That is, the error rate for each one of the years is not significantly different. Of course, we do have that 5% alpha risk. All right. In this video, we saw how to use the chi-square test statistic and distribution to test 4 population proportions and see if they were equal or not. All right. Next video, we're going to see one more awesome use for chi-square when we test the independence of 2 categorical variables. All right, we'll see you next video.